Okay, so to answer the first question, to solve for our acid concentration, our base concentration, and our pH. So we're given in the problem that our pH is equal to or roughly equal to 3.20. To solve for our acid concentration, that is simply base 10 to the negative pH, which essentially comes from the equation that our pH is equal to negative log of H plus, or our acid concentration. So in this case, we have our acid, our hydronium, which we would set equal to 10 to the negative 3.20, our pH, and that gives us a result of as 6.31 times 10 to the negative 4 molarity. So that's the concentration for our acid. Now we can solve the concentration for a base, or OH, by using the equation or the conversion factor for OH is equal to Kw over H plus. This is the same thing to solve for acid concentration. We would just do Kw over OH. But since we're solving for OH, we would do Kw over our acid concentration. So 1 times 10 to the negative 14 over 6.31 times 10 to the negative 4 molarity is equal to 1.58 times 10 to the negative 11 molarity. Now to solve for our pOH, that is simply our 14 minus our pH. And same thing goes for pH as well. This case we're solving for pOH, so it would be 14 minus 3.20 is equal to 10.80. So to answer the second question regarding the pH and the formic acid, our formic acid is the HCOOH, and that formic acid dissociates into the proton and its base. So we're given the Ka and the initial concentration in the problem. So we can set up our ICE table using the initial concentration that we're given of the formic acid, 0.16. Since we're not given the concentrations for our proton and our base, we assume those are 0. Since we're going to be forming products, our formic acid is negative X for the reactants and positive X for our products. So then we get an equilibrium concentration 0.16 minus X and XX for the products. So then we can use our X squared over our 0.16 minus X. We set that equal to our Ka value. Use the 5% rule to cancel out the X. The X is going to be equal to our square root of 0.16 times the 1.17 times 10 to the negative 4, or 1.77 times 10 to the negative 4. That is equal to 5.3 times 10 to the negative 3. So that is our X value. Now, since that is our X value, that is also equal to our proton concentration. So H plus is equal to X, and our pH is equal to negative log of H plus, which we also found from question 1. The equation from question 1, so our pH is equal to negative log of 5.3 times 10 to the negative 3, and we get that a pH is equal to 2.27. To calculate our percent dissociation, we have our proton concentration, which was our 5.3 times 10 to the negative 3, over our formic acid concentration, which was 0.16. We divide those two quantities and multiply by 100, and we get that our percent dissociation is equal to 3.31%. So when comparing gastric acid and formic acid, we can see that our gastric acid, which is primarily composed of hydrochloric acid, has a higher concentration compared to formic acid. This gastric acid also has a relatively low pH, and it is a stronger acid since it is primarily composed of HCl, a strong acid, hydrochloric acid. So this will lead to a more acidic substance compared to formic acid, which has a smaller concentration and it is a weak acid, having a higher pH compared to gastric acid. So overall, formic acid will have a smaller dissociation activity for the substance overall compared to gastric acid. Question 4, we know that sodium hydroxide is a strong base, so it goes to full dissociation. In the problem, we are given our hydroxide concentration, which is 1.2 molarity. So to calculate our potential hydroxide, our pOH, that is going to be equal to negative log of our hydroxide concentration, 1.2, which is roughly equal to negative 0.079. And this is actually the same thing. pOH for calculating, this is the same thing as calculating pH. It's similar. We would use the negative log of our acid concentration. However, in this case, we're using hydroxide. So to find our pOH, so we're using the hydroxide concentration. Anyway, so that is equal to our negative 0.079. And our pH would be equal to our 14 minus our pOH. So 14 minus our negative 0.079 is equal to 14, roughly equal to 14.079. To calculate the pH given a molarity concentration or the concentration of a base, we can write our reaction. So for NH3, it would be the nitrite plus water yields the ammonium plus the hydroxide. And this is our reaction that we would use to set up our ice table. So from here, when we set up our ice table, we would do our 1.2 is our initial concentration for our base, NH3. Our change is negative X since we are forming products. And this would be, the products would be plus X. And then we could solve for X by setting the X squared over 1.2 minus X equal to our KB, which was given in the problem, 1.76 times 10 to the negative 6. So our X is equal to 1.2, the square root of 1.2 times our KB, which is equal to 1.4 times 10 to the negative 3. So that is our X value. And our OH is essentially equal to our X as seen in the ice table. So now we can solve for pOH, which would just be our negative log of our hydroxide concentration. So we know that that's X, so we can say that our pOH is negative log of 1.4 times 10 to the negative 3. Our pOH is roughly equal to 2.85. And then our, let me just change the color here. So our pH would be equal to our 14 minus our pOH, 2.85, which is roughly equal to 11.1. So when we compare our sodium hydroxide and our nitrite or NH3, we know that sodium hydroxide is a strong base. So it has from the previous two problems, it had a higher molarity concentration compared to NH3. So, and that makes sense because a higher hydroxide concentration will indicate that more base is present in the solution, which would thus indicate a higher pH. It is going higher on the pH scale, reducing the amount of proton concentration in the solution. So it's a more basic solution compared to NH3. So the opposite is said for NH3. It has a lower concentration. It is a weak base. So a lower hydroxide concentration will indicate a lower pH, which indicates a more acidic solution. So when we talk about treating the fire ant bites, we can actually think of this in terms of a reaction. So we have our acid, our formic acid, and our soap, which is basic. So that would be our base essentially. So whenever we're adding base to an acid or acid to a base, we can think of Le Chatelier's principle because the reaction is trying to reach equilibrium. So since we already have a high amount of the acid, the formic acid, when we add a base to this acid, it will try to neutralize the reaction. So we have like our acid, the formic acid plus our base, our soap, will yield our conjugate base and conjugate acid. And when this reaction reaches neutralization, this will lead to the relief from that burning feeling, that burning sensation coming from the fire ant bites, because reaching that neutralization will mean that we are near a pH of 7. And our body pH is actually close to 7.4. So when we try to reach close to that pH of 7, we are reaching close to that our body pH, which is 7.4. So that is the neutral state, and that will by adding the soap, by adding our base, that will further reduce the proton concentration overall in the reaction, which is essentially causing the burning sensation, and that will lead to the relief from that burning feeling from the neutralization reaction using Le Chatelier's principle.